This is a bassoon. It's a double reed woodwind instrument that has a very characteristically warm and longing sound. Despite the simple sound, it's actually very, very complex, having over 30 keys and tone holes to manipulate the pitches it produces. And standing a total of 4.5 feet tall, I measured that it actually has about 106 inches of total tube length. Now remember this number because it's going to come in handy later. Now, to make sound on the bassoon, you need a reed, and specifically a double reed. A double reed is 2 pieces of cane bounded together with 2 pieces of wire and a head of string. By creating a seal around the reed, like so, with your mouth, air passes through the 2 reeds and vibrates, creating a very high-pitched squeaky sound. But interestingly, you can almost play a scale just with the reed by changing the speed of your air and the pressure of your lips and embouchure. Next, by taking the reed and attaching it to this metal thing on the bassoon called the bocal, the high-pitched frequency created by the 2 vibrating reeds gets sent down the length of the whole entire bassoon, 106 inches if you cover all the holes, and creates a very warm, nice sound. Also, by increasing the length that the wave travels through the bassoon by covering more holes, you actually get a lower frequency that comes out. Now, let's demonstrate this with some calculations.
Let's try this with a hypothetical length, L, of 1 inch. Here are calculations with L, 10L, and 100L. Let's refer to the equation L equals half lambda, since, as an example, this is the simplest wave with 2 open ends. With a standard airspeed of 500 inches per second, for example, we can use the equation V equals F lambda to find the frequency that each length would produce. Remember, since we are trying to prove a pattern, the speed is a constant here and doesn't necessarily matter as long as it's above 0. As you can see, once we do the calculations, it seems that the tube length is inversely proportional to the produced frequency. So the bigger L gets, the smaller and lower the frequency gets. This pitch is called G1, and this is G2. They are both the note G, but 1 octave apart. One would think that 2 different notes should have 2 different fingerings, but G1 and G2 almost have identical fingerings. The G2 fingering is exactly the same as the G1 fingering, apart from a small tone hole leak called a half hole, right here. This leak plays an important role in which we are going to discuss. So, what's the science behind this? Well, it's harmonics. G2 is actually the second harmonic of the fundamental frequency, G1. Fundamental harmonics in open tubes are waves that look like this, and are modeled by the equation lambda equals 2L. The second harmonic looks like this, and is modeled by the equation lambda equals L. Notice the difference between the two. If we just look at one of these waves, the fundamental frequency has 2 antinodes, 1 at each end. On the bassoon, this would be where the reed meets the bocal and where the farthest finger hole is covered from the G1 fingering. Notice how the second harmonic frequency has an antinode right in the middle of the original length. Could this antinode be the leak created by the half hole?
Let's see. I measured that the G1 fingering covers enough holes to make the length of the tube 53 inches long.
We use the fundamental equation discussed earlier to find that lambda equals 106 inches. Hey, that's the total length of the bassoon. Because we know this length creates a frequency of G1 at 50 Hz, we can plug that into the standing wave equation to find the same airspeed used, which ends up being 5,300 inches per second. Next, let's use the same airspeed value for the second harmonic. The fingering length is still the same as G1, and the tube length hasn't changed, still being 53 inches. If an antinode is present at the halfway length, at 26.5 inches, the second harmonic will be allowed to form, hypothetically. Now, measured in real life, the half hole is present around 26 inches from the bocal, which is halfway through the length. Plugging this into the second harmonic equation, we see that the wavelength equals the total length of 53 inches.
Obviously, I can't do math here. 26 plus 26 is actually 52, and that would be the wavelength with an antinode halfway through it.
So, with some quick math, the frequency sounded is about 101.9 Hz, just 1.9 Hz above the note G2 at 100 Hz.
So yes, because of the half hole, we jump from playing a G1 to a G2 by shifting a finger to create an antinode halfway through the covered tube, which sounds the second harmonic. To confirm that this works, let's try jumping to the third harmonic using the same G1 fingering but creating an antinode either a third or 2/3 of the tube length.
1/3 of 53 is 17.67 inches. So if we create an antinode with a hole around 17.67 inches away from the reed, we should be able to jump to the third harmonic, which interestingly sounds a D2, a perfect fifth above G2. Now, again, measuring about 18 inches away from the reed, there is in fact a hole. Let's use the same G1 fingering, but open that hole and see what happens.
Hey, it actually works! But what are harmonics, and why are the first and second harmonics the same note, just an octave apart, but the third harmonic is a perfect fifth above the G2, sounding a D2? This is due to the harmonic series. The harmonic series is a sequence of tones represented in the form of sinusoidal waves where the sounds are all integer multiples of a fundamental tone. So all the waves fit into each other, like so. The more antinodes you create, the smaller the wavelengths become, and the higher the frequency gets. So the higher the harmonic, the higher the pitch. So why does this matter? Well, on the bassoon, this means that we can create new fingerings for pitches. In fact, the higher register of the bassoon is entirely built off fingerings from fundamental frequencies at the bottom of the respective harmonic series. And we can do that by adding antinodes in the respective places where they would be on the actual wave. So if we wanted the 7th harmonic, we would put antinodes every 7th of the length, although that would be very, very difficult to play and very, very high. To recap what we learned today, first we learned what a bassoon was and how it worked. Then we found that tube length was inversely proportional to the produced frequency. Next, we discovered how harmonics and the placement of antinodes can sound different frequencies. And finally, we discussed the harmonic series and applied it to creating new bassoon fingerings. Thanks for watching, and I hope you enjoyed.